So I'm going intense this day. I'm back one more time. My name is Mr. Steele. I'm going to be working through another question or problem style or problem type on your ESQ model for the first half of Honors Pre-Calculus. And in this video, we're going to be talking about function values and tables, basically reading function notation, as well as using function composition and a numerically represented function in order to evaluate some expressions. I would say that this is probably the quickest, cleanest, and I don't want to use the word easy, but the easiest of all the questions on the essential skills quiz that you're going to be facing. It involves, I think, the least intensive work, but it does involve some careful reading of the problem. It's very easy to reverse things, to forget which function describes which, so paying close attention to detail will be really helpful here. With that in mind, let me talk through a couple key ideas and then do the 4 quick problems that are on here. So to kick things off, key ideas here, this is sort of by virtue of being one of the simpler and less work-intensive problems. There's not a ton of extensive key ideas for me to address here, but there are 2 I wanted to at least highlight so that way, again, they're in your head. That's always the purpose of this first little section. And the first of those ideas is composition. And first of all, composition or function composition is what this question on your ESQ is effectively evaluating. It's your ability to read the notation of function composition as well as to, of course, evaluate expressions using different representations of functions. So in function composition, what we mean effectively is a function inside of a function. So what you'll typically think of that as is something like f of g of 4. And the idea here is when you go to evaluate this, this has a function being evaluated at another function's output. So specifically, if I write it this way, you can see that effectively you have to figure out what g of 4 is so that then you can plug in whatever g of 4 is to f. So for instance, if g of 4 was equal to 10, then this expression would be equivalent to f of 10. So the idea here is you've got to be able to read which is which. Now here I'm just writing out like expressions, but on the problem itself you'll be given a function maybe represented algebraically. So on the example we'll see there's a linear function that represents f of x. You might be given something graphically. In other words, they could give you a graph with some points labeled and you'd have to read function values out of that. Or it could be represented numerically, which is presented in a table, which is also something that shows up on the ESQ model. The idea, though, is you'll have to evaluate the expressions in there, working inside out. That's almost always the best strategy to approach it with, and then being able to sort of like navigate between the 2 function types. So really, though, this is a question about function composition and notation for that function composition. The second thing that's on here isn't really a concept, but it's something that appears on the ESQ model that I think sometimes can kind of throw you a little bit. And so I just wanted to make sure that I addressed it once before we get to the relevant problem, which, by the way, I think is the 4th one in this section on your ESQ model. And that is, how do you evaluate an inverse expression? So basically, to kind of help you see this, what I'm talking about is an expression that looks like, I don't know, g inverse of 5, let's say. Let's say you're asked, or you at some point in a problem have to evaluate g inverse of 5. Well, let's say that you are given an xy chart, and I'll do a really, really short xy chart here. I'll just give you 2 function values. So this is x and g of x, so not g inverse. Let's say that we have 1 and 3, and we have 5 and 2. So basically, if we want to figure out the value of g inverse of 5, that's like asking what x value pairs with 5. And looking at our table, we can see that when x equals 1, g of x is equal to 5. That means g inverse of 5 is equal to 1. And now having said that, like as soon as you see it, you're like, okay, yeah, that makes sense. But let me just illustrate why it is that that makes sense using the meaning of inverse. So if I tell you g inverse of 5 equals 1, we could undo both sides here, let's pick a good color for it, by taking g of both sides. So g of g inverse, because those are inverses, undo one another, or you could also think of it as just what that's equal to, but g of g inverse will cancel out by undoing one another, and we'll get 5, and of course then we have g of 1 on the right side. Notice, of course, g of 1 equals 5. That matches, therefore our value is correct. So as a heads up, when you're evaluating an inverse expression here or wherever, you've got to think about sort of what that means and how do we go backwards from the output to whatever the original input was. This is just a way of phrasing here's my output, tell me the input. So with those two ideas in mind, I think you have more than enough to dive in, with full force, full strength into this question on the ESQ model. So let's do that. So starting at number 1, I fear that this is going to go so fast that it's going to be almost a waste of time. But I think we can make this work. So first of all, what are we given? And this is true for all 4 of the parts, so I'll go a little more extensive here. But we are given 2 different functions in this problem. We are given f of x, which is 2x minus 5. So basically we have 2x minus 5 up here. It's a linear function, slope 2, y-intercept negative 5, but it's just something we can plug into really nicely. And then second, we have g of x, but g of x is given in the table. So basically g of x is right here. So we'll be reading values out of the table. Our task in this first problem is to evaluate g of f of 3. So just to use our color a little bit here, let's represent this a little bit differently. I'll write this as g of f of 3. And we want to figure out what that's equal to. What is the numeric value of this expression? Which I think we're going to come out with a numeric value every time this time, or in this problem. So let's see, what do we do? Well, to kick things off here, our strategy basically amounts to working inside out. It's like that Pixar movie where the emotions are alive. Basically, we're going to work inside out, and by that I mean let's evaluate the inner function of the composition first. So our first question becomes, what is f of 3? Well, we can figure out the value of f of 3 by using the functions formula that were provided. F of x is 2x minus 5, so f of 3 is going to be 2 times 3 minus 5. That is, of course, 6 minus 5, which is 1. That is to say, our expression, g of f of 3, is equivalent to g of 1. Now, since we've already evaluated the inside part, we now just have a singular expression to evaluate. We just need to know what is the value of g when x equals 1. And we can, of course, look up at our table of values to do that because our table involves g. G of 1 is equal to 7. Therefore, g of 1 is 7. Therefore, g of f of 3 is equal to 7. We start inside, evaluate that expression or the function value that's asked for on the inside, and then we evaluate the outer part of the composition, and we get our value. G of f of 3 is 7. And we were able to bounce between those two functions with no issue whatsoever. Question number 2 is going to be the exact same process as number 1. So we're going to follow that same strategy that we did before. Just like last time, let me set this up. I'm going to do light blue for f and green for g. So I should underline it like that. So looking down here, we're trying to evaluate what is f of g of negative 2. We want to know what is this expression equal to. Like when we perform this composition, what do we get? Well, we'll do the same thing we did last time. Let's begin on the inside. So the first question becomes, what is g of negative 2? And the answer, of course, depends on g of x, and g of x is represented numerically in the table up above. We look for negative 2, and then we find g. So g of negative 2 is equal to 9. That means what we need to evaluate here to know the value of f of g of negative 2 is to evaluate f of 9. And looking up there, the rest of this problem is pretty trivial. Looking at our expression, f of x is 2x minus 5, so f of 9 is going to be 2 times 9 minus 5. So let's just get that color in there correctly. And of course, 2 times 9 is 18, minus 5 is 13. So 13 is the value of f of 9, which is the value of f of g of negative 2. So once again, we navigated that composition by working inside out, and then very easily evaluated this. Like I said, moves really quickly. Now question 3 is probably even simpler. We've got g of 5. So we've got the same function there. Notice, by the way, that these aren't inverses, so they're not undoing each other. We're not going to get rid of either of these expressions through sort of like mathematical inverse properties. We've just got to evaluate it twice. But the good news here is that once again, we're just evaluating a functional composition. So in this case, even though it's the same function twice, I'm going to write this as g of g of 5. We want to figure out what is this equal to. Well, we'll follow the same strategy that we did before. G of 5 is our first task. So what is g of 5? Well, looking up at our table, there's the appropriate section. When x equals 5, g equals negative 2, so g of 5 is equal to negative 2. Therefore, when we try to evaluate g of 5, we're really trying to evaluate g of negative 2. And our question then becomes, what is g of negative 2? Well, we've actually used this value already in this problem, but that's okay. We'll go back to our table. We'll see that when x equals negative 2, g of x is 9. Therefore, g of negative 2 is 9. And ultimately, g of 5 is 9. Or g of 5 is 9. I was trying to say it like, gee, golly. But yeah, I don't know if that joke landed, but that's okay, because the question was really fast. This is the kind of one where I'm like, so I'm going to actually look at this one, and maybe. It definitely looks trippier than it actually is. And then finally we have our last one. And I will say that I think it's like timely, because this last one at least has that little extra challenge built in here of g inverse of 8. So we've got a little bit of something extra happening here. Once again, though, we're using the functions f and g. So basically our job, or our task in this case, is to evaluate f of, it says, g inverse of 8. So the question is, what is that equal to? And I sound like a broken record, not that I've listened to a lot of records in my time, but basically where I need to begin is with the inside. We work inside out when we're dealing with evaluating compositions. So our first question is, what is g inverse of 8? Now we talked about this really briefly in the key ideas section of the video, talked a little bit about what this means, but basically this is asking us what x value outputs 8. This is basically a different version of the question. It's asking for the input given a certain output. So looking up at our table, we can quickly identify that g of negative 3 equals 8. Well, if g of negative 3 equals 8, then g inverse of 8 equals negative 3. Therefore, g inverse of 8 is negative 3. So basically, we've got the inside value then. So now instead of evaluating f of g inverse of 8, we can think of this as just being evaluation of f of negative 3. And now we just need to evaluate the function f at negative 3. Well, fortunately for us, we can see what f is. It's still that line, 2x minus 5. So 2 times x minus 5, and that x is going to be negative 3. So cleaning this up ever so slightly, we're going to get negative 6 minus 5, which equals negative 11. So in our case, f of g inverse of 8 is going to be equal to negative 11. And once again, we've navigated a function composition, even one that involved an inverse, like being kind of like dropped in for some variety. And yeah, that ends the video. There's nothing more to say here. As I said, I think this is one of the quickest problems. I think it's one that's really testing your ability to be fluent with notation as much as anything else. There's not going to be tricky algebra here. You're just reading functions and keeping your work organized so that you keep track of which function is which, and so that you're applying the right rules each time. But basically in these 4 problems, we got to see these ideas come to life. We got to see function composition and learn to navigate it with the inside-out strategy, working on the inner composition or the inner function evaluation first before moving to the outside one. And we also saw in that 4th problem only, but just it's still valuable there, how it works when we have to evaluate inverses, and basically how we're given an output instead and needing to find the input. With that in mind, we did our 4 composition problems, and there weren't really a whole lot of hiccups that we ran into. So I'm not overly concerned about this one. I think you're going to do pretty well. I imagine this is going to be the least viewed video of the series, but that's okay. It's just nice to have the resource available for you in case you need it, or in case this is sort of a hole in your understanding. Regardless of whether it is or isn't, that's going to conclude this video. I have nothing more to add. I think that I've left it all on the table here. The table of values. Okay, whatever. Yeah, that's going to conclude video number 8. Thanks for watching. I hope you got some good value out of this if you were tuning in. And yeah, I'll see you tomorrow, but that's not necessarily true. But yeah, it's also probably true because I'm probably going to do question 9 and 10 tomorrow. But we'll see. Like, who knows what the future holds. But I do know what the immediate future holds. I'm stopping this video right about